Welcome to Network Engineering. This is Chapter 4, Part 3, where we talk about IP version 6. So, there's a lot to say about IP version 4. There is some to say about IP version 6, but I'm really hopeful that this lecture will be a lot shorter. So, I apologize for the length of Part 2. Anyway, IP version 6 tries to fix all of the evils of IP4 and make a bunch of new features that we couldn't even have dreamt about back in 1983. So the first thing is we're going to move to 128-bit addresses. We maintain the ability to do unicast, multicast, and broadcast, but we also add anycast to our options. And if you remember from Part 2's lecture, Anycast means that I can say I want to send to this IP address, but it could be any one of these computers. I don't care, pick one. And so that anycasting is really a useful thing. So it's not as, I haven't done any research to see how often it's been taken advantage of, because I feel like it's pretty new, but it's really exciting. I could think of a number of options or ways of using that. One of the first things that they did in IP6 is they ditched the variable length header. And let me tell you, that is awesome, because now we have exactly 40 bytes no matter what you're sending. Always 40 bytes. There's no options, there's no variability, nothing. And we got rid of the 16-bit sequence number and moved to a 24-bit flow label. So with flow label, what this allows me to do is when I send out a packet, I have 2 to the 24th or 16 million simultaneous flows that I can describe to the router. And the router can use that to keep track of which flows are going in what direction. And that's a lot of different flows. And that's 16 million different flows within one combination of source and destination address, which is just kind of crazy. Fragmentation is completely gone. What we're going to find is if I send a IP version 6 datagram and it's too large for the medium that I'm sending, I'm going to get an error back that says this is too big. So then the sender is going to say, oh, okay, I'll resend, but this time with a smaller IP size. And it doesn't take much to figure out what the right size is. In fact, what we could do is the binary search trick. So with that spending forever here, let's say I pick a size that is 16K. And it comes back and says, I can't handle 16K. So then I have it. And it comes back, so I have it and it's 8K. And the router says, I still can't handle that. So then I drop it one more time to 4K. And the router says, nah, I still can't handle that. I go down to 2K, and now the router says, I can handle that. Now the question is, could I handle something bigger? And so here I dropped 2K. So what I'm going to do now is I'm going to send my next frame out using a 3K packet. So I'm going to have this distance. So 2K plus 1K equals 3K. And if the router comes back and says, no, I can't handle that, now I know that the largest packet size that the router can handle is between 2K and 3K, so I'm going to drop it by half again. So this was 1, so now I'm going to drop it by 512. So this would be, I'm going to send out a 2.5K packet. And if the router comes back and says I can handle that, then I'm going to try to split the difference here between these two, and I'm going to send 2.75K. And I'm just going to try to kind of titrate my way around to figure out what is the most amount of data that I can shove into the router's throat before it coughs. And so by doing that, we can maximize and dynamically tune the size of the payloads, or we could just assume that everything's going to fit in 1500 bytes. And if it doesn't, we'll drop to like a predefined rule. So there's a bunch of different strategies. The mechanism here is just saying we're not going to fragment, but we will tell you if we've gone too far. So every operating system now is free to implement a strategy to find a block size that works and then go with it. The binary search is just one way. We've also gotten rid of the header checksum. That's gone. Why? Well, communications protocols are more reliable, so there's no not as much reason to check that checksum here. And both UDP and TCP both have checksums, so we don't need another one. So get rid of it. And again, there's no options. Instead of sending options, what we can do is send special ICOMP or Internet Control Message Protocol messages and say packets with this flow label get this option. And so we can send those as separate messages, and then this actually gives the routers a chance to respond back to us and say, yeah, I accept that option. And again, the operating system can negotiate with those IP6 routers and get the best traffic we can. Yes, there was an IP version 5. It was the basis for an internet streaming protocol that predated voice over IP and ATM networks. It was experimental, it never got off the ground, and unfortunately it was being experimented with in between the time that we did IP4 and 6. So it already had a name, people were already using it, we thought it might be going somewhere, and then it went nowhere. IP6 addresses are 128-bit, and instead of doing them as dotted quads where we do decimal, it just doesn't make any sense. The numbers are too big. So instead, IP6 are represented as what are called hexatets, 16-bit values, and then there's going to be 8 of them. And we could start off with a full 128-bit address. That's how big 128-bit looks. It is a big number. But there's a shorthand that we can use to shorten this up. And the first thing we can do is we can remove any leading zeros. And so, for instance, I can rewrite this address by getting rid of that leading zero and those leading zeros to get that. And we still have another rule to make this even better. I can delete one consecutive section of zeros and replace it by colons. So I could take this whole string of zeros here and turn them into just a double colon. And so that makes things a lot better. And a lot of these addresses are so sparse, like there's a lot of zeros in them, that it just makes sense. We'll be able to shorten things up a little bit easier that way. It should be interesting to note that, for instance, right there is a 32-bit number, two 16-bit numbers. Already, right there in just the last little bit of this, I have more space than I did in all of IP version 4. I mean, that's just how big these things are. Just kind of crazy, right? But the trick about this is we can only do that rule once. And if you think about it, let's say that I wrote this, FD : AD : 24. All right, so I have no idea how many zeros go in between here, right? This is a 16-bit value, this is a 16-bit value, and that's a 16-bit value. So I have 48 bits, and if I subtract that, I have 80 bits left. And so I could have any combination of bits that wind up adding up to 80 in those zeros, and they would be completely different numbers. You know, I could have FD 0, 0. I'm just going to do individual zeros. 0, 0. So each one of these is 16. So 0, 0, 0, AD 0, 2, 4. Or I could reverse that, like any combination of those. And there's just ambiguous. So we can't do that rule twice. Not allowed. But I can do it once. Now if I think about why can I do it once, well, this is a 16-bit. There's another 16-bit. There's 3, 4, and 5. And we need a total of 8. So how many bits of zeros do I have? I have 3 groups of zeros, 24 bits. Oh, sorry, 48 bits. As another example of how this works, we could take this number, apply the rule number 1 to get rid of leading zeros, so those two go away. those two go away, those three go away. And then we can apply rule 2. And in rule 2, I could do the 2001 and I could delete those. Oh, this isn't right. Let's see. So this would be 2001. I could skip over those. DB, there needs to be 0:0 in there. I forgot to type that in. So I could do that, or I could delete those two leading zeros, but I can't do them both. It looks like I tried to do that. So don't make that same mistake. So those are our IP6 addresses. So right off the bat, they do look a little intimidating just because you have to know hexadecimal, but hopefully by now you have become a Zen master of the hex. One other trick about IP6 is that every interface gets its own link local address. And that address is only valid for the network segment between that interface and its router connection. And IP6 is going to use a special range. It's going to use a range that starts with FE80 and then a whole bunch of, in this case, 54 bits of zeros. And then the bottom bits are all going to be, the bottom 64 bits are going to correspond to some unique device address. And oftentimes it's going to be the device address of the network card, or what we call the MAC address. But we found that we don't want to make that information widely available, so we'll make it a secure hash of a MAC address that fits into those 64 bits. So right off the bat, every network device can just turn on and create an IP6 address with FE80 and then 64 bits of crap at the end. And I could actually start talking on the FE80 network without any further configuration. That's kind of cool, right? IP6 uses additional features that include a hierarchical address assignments, just like what we saw for IP4, except that the assignment of networks can create what are called super networks. So you can imagine Comcast using IP6 is assigned one super network address. And then Comcast, as far as the entire world is concerned, needs to have exactly one external entry to represent all of Comcast's network, including its customers, its TVs, and everything. And then there's no need for a CIDR subdivision, right? So externally, that one super network can be used to get everybody. Multicasting can be built right into the subnet. I don't need to have those special reserved addresses. We can multicast or anycast right within the IP6 address range that's been defined. So again, a media company like Comcast could put servers all over the place and allow you to anycast into their content delivery. Stateless addressing auto configuration. So that FE80 link I just mentioned, if no other routing or information is present, Slack would allow me to send a message out over that and say, hey man, is there anybody who has any information about how to get the internet? And somebody would respond, maybe the router would respond and said, yeah, I do. You can talk to me on this IP address. And so without any need for DHCP or manual configuration, IP6 can Slack and auto-configure itself without any further intervention. That's a big win over IP4. But wait, there's more. Using the neighbor discovery protocol, nodes can issue broadcast requests using Slack, and they can actually get the rest of their network configuration that everybody else is using. So for example, I can get the addresses from domain name lookup services, I can do host names, I can do find my routers, I can find other machines on the subnets, I can find those anycast addresses. I don't need to have DHCP or anything else in an IP6 environment, as long as one machine can provide the necessary configuration. The neat thing is the router can be like the Eye of Sauron and watch what's going on. If the router doesn't respond, but it watches somebody else respond with fake information, it can disable that bad host. And so very quickly identify this guy's trying to disrupt the network service. So that's also really handy. Internet Protocol Security, or what's called IPsec, and IKE, the Internet Key Exchange, are both built into IP6, and they allow special header types to be completely encrypted and decrypted between routers. And so it's possible that as a frame is moving from one router to another router, that there can be a key between those two routers, and those communications can be encrypted between them. The receiving router would decrypt and then re-sign and encrypt the network for the next link. And so if somebody were to do a man-in-the-middle attack, we can defeat that completely. It also makes it really hard for people to watch your traffic if they can't decrypt your datagrams. Simplified routing, so the headers are greatly simplified, so it's not hard to make a 128-bit computer today. There's no checksums, there's no fragmentations, there's no options. All the data is in the same place. I can literally load it into memory, pick out the bits, and route. Greatly simplified over IP4. Mobility, I can move entire subnets without disrupting global routes. All I've got to do is put every device onto a subnetwork of a super network, and then just move the subnets around as they move from cell to cell to cell. And so what we'll find is cell phone networks use IP6 extensively now, because I don't have to try to fake address route things. I can literally just let your device migrate through the IP6 super network and give you a whole subnet of ranges, and it works just kind of like magic. And your phone can just slack, right? So if you suddenly lost complete connection and you pop up on a different device and you Slack auto configure, the router can see that, phone home, and say, okay, I've got this device. And now all of a sudden your traffic has followed you to the new cell, built into IP6. Jumbograms. IP6 can allow up to 4 gigabyte packets. So you want to send a big chunk of data all at once over some special link, knock yourself out. That's a pretty big chunk of data. Although you'd need the link layer underneath of you to be able to support that. Most don't. As an example of how all this works, so I said Comcast has been assigned a SuperNet. So it has 2601:980:0/32. And so what that means is the first 32 bits are assigned to Comcast, and that gives them 96 bits of addresses, or 2 to the 96th unique addresses that they can give out within their subnetwork. So as far as the world is concerned, to get to any Comcast device, I only need to route to that one destination. Then Comcast can subdivide this, or has subdivided this, so each customer is assigned their own 32-bit address range. So for example, I might be assigned C100:35. So what this means is when I get a route from IP6 on Comcast, I get a route of 2601:980:C100:35:1/64, meaning I have another 64 bits of space available to me. Why is that not 32? Oh, yeah. So they're reserving 32 bits for each customer. It allows them 4 billion customers, each with their own 64-bit subnet. I mean, that space is huge. I mean, think about that. Comcast can have one subnet for every customer and have more subnets than are available on the global internet today. So without using NAT, this is wrong. Without using NAT, subscribers can have 2 to the 64, which is 1 times 10 to the, I forget, 2 . 2 to the 64 is 1 times 10 to the 19th. Wow. 1 times 10 to the 19th machines at every location. That's 32 times, no, more than 32 times. That's exponential growth, you know. It's like having 4 billion internets at every Soho location without having Comcast having to know about anything beyond just that one customer number. So even Comcast internal routing is more efficient. And I'm willing to bet, like if you were to look at a region, probably everybody in a region shares the first prefix. So probably everybody in Shippensburg shares the C100. All of my neighbors who have Comcast are probably somewhere in that range. So you can even use a hierarchy within a hierarchy. If I was Comcast, I certainly would have done that. So then without using NAT, you have all of the subscribers having more machines than on the internet, and then there's no reason to even use NAT, and so we don't. NAT6 is stupid if you're on IP6. So if locally each interface is given a SLAC address, it's going to pick a SLAC address that is a form of its Ethernet address. Stupid telemarketers. Okay, so anyway, so clearly we can make up an address, and I do use DHCP at home, and my DHCP server does give me an address that I can control just to keep things easier. And so each of the machines, I give out a 16-bit local machine address to all of my local machines. In that way, I can give them a name and I can give them a fixed IP address, and then they can communicate. IP6. So IP6 does have some address classifications like we saw with IP4, but they're a little bit easier to use. For example, IP6 allows a unicast address. And so this is a single machine talking to another single machine. The prefix here is greater than or equal to 48 bits. We have a subnet that has to be less than 16 bits, and that has to leave 64 bits for the local interface. So we've already seen that with subnet, with Comcast. We can have a link local, and so this is going to be that FD00, that 10 bits, or sorry, FE80, and a bunch of zeros. That's the link local format, and then we can have an interface address of 64 bits. And then with multicast, we create a special address that is got a prefix, a flag, and a service agreement. And then we pick a 112-bit long group ID. And the odds of picking the same group ID are 1 in 2 to the 112. Like, good luck picking the same group ID as somebody else. So multicast is globally routable. And so theoretically, if you're Netflix, you could theoretically multicast out to everybody the same stream of data. Probably not Netflix because they don't do stuff like live events, but if you were, say, Twitch does a lot of live streaming, and so Twitch could literally send out a single stream from their servers, and then everybody who subscribes could just ask the routers, please let me have this multicast prefix and group ID. That would propagate to the next router or the next router until it got to Twitch, and then all the routers in between would just stream. As Twitch sends once, it would stream out to everybody who's asked for it, and it would just kind of magically work. Multicast is cool when it's configured properly. IP6 does add a complication. Web browsers can't tell an IP6 address. So instead, we have to add a new format if you want to go to an IP6 address without using the name. So you would do an HTTP:// brackets around the IP address. The colon is used here in an IP, in a URL for setting the port number, and that's why we need the brackets. So anyway, that would be if you're going to use an IP6 URL. IP addresses also have this bizarre format when they're in a URL called scope, and this is really a BSD thing. It's not against the standard, it's just they're the only ones who use it. They can identify what interface you want to use by using that link local address, the FE80, and then in the hexatet right next to it, putting the interface number that you want to use. So interface 3 corresponds to ETH2, so I want to use that link to get to that local address as opposed to some other link. Most other operating systems don't pay attention to that. So I should just add, that means that there'll always be zeros there. But BSD, and since OS X started off as a BSD type of Unix, it has the same type of thing. So does iOS. Apple iOS. Anyway, there are some special IP6 addresses. That ::/0 is the default route. It means I don't know how to get it to the next hop, so send it to your best guess. A ::/128 is the unspecified address, so you use that in software when you just don't know where to go. And typically either the router has a rule to handle it or it gets dropped. You also can have a ::1/128 insider form that says localhost, that is this machine. So that t-shirt that says there's no place like ::1/128, extra cool because that means you're cool enough to know about IP6. The ::FFF whatever, we can embed an IP4 address in those 00s. We can do the same thing in the FFFF 0000 to translate from one to the other. We can also do another version of that in 64. So there was a number of different strategies used for mapping IP4 into IP6, hopefully as a transition, and none of them have really taken off so well. So beware if you try to expect to use those, just do a little research to make sure that they work. The Teredo tunnel and ORCID are kind of protocols that are used for, again, tunneling through other routers. So again, you can see if those are supported or not. 100::/64 is the discard. It's like Unix's dev null. It just means that we can route to that and it's just dropped. So if you needed to like have a black hole, be really funny if you have like somebody on the internet, some noob on the internet, and you're like, man, yeah, you just open an SSH session to 100:::, and then a bunch of data, and they think, oh, cool, this is where all the good hacker stuff is. And of course, they get nowhere. Let's see, they got smart. And so if you're going to do documentation, like for teaching, and you want to provide an IP address 6 address, you're supposed to use the 2001:DB8. That would be the documentation address. Or for like Cisco training and stuff, you'll see that pop up all the time. FE80 is that link local that we just talked about. FE00 is the same kind of thing, but for networks. And then FF00 is that global multicast, and then all of those other fields apply. So, without doing a whole lot of demonstration on IP6, there it is. I should point out that our campus doesn't really fully support IP6 yet. So let me just give you a quick explanation of that. So if I'm here on my own machine, let's see, I go to Sloop. Yeah, I cannot type today. So if I do this ifconfig command, which is something I think we've seen before, what it shows me is the IP configuration for each of the different interfaces that Sloop has. And we see that Sloop has an IP4 address, like so. Look, there's the net mask that we learned about in the previous video. And we see here that it has an Internet 6 address. And that FE80, well, that was that link local. That's the one that it just kind of made up all on its own. And it almost looks like, you know, we can see some of the elements of the Ethernet address. So there's the 56, there's the 21, there's the 89, but then they stuck an FE, FF in the middle of that. There's the 56, there's the 50. So, you know, it doesn't look like it's all that secure of a hash, I'll be honest with you. But the Ethernet address is used to make up the link local address in Linux. If I were to do the same command on a, let's say, a Windows machine, the IP6 address is going to be completely transmogrified by the as an INET 6 address. But that's it. There are no other IP6 IP addresses given here. All right, so anyway, so we don't get IP6 routes to our campus. If I were to take a look at my own local machine, so this is a Windows machine on my home network, and here I can see that I do in fact have, this is the 2601.980 is Comcast, there's my customer number, and there's my local address from my router through DHCP. Here is the same guy from a Slack configuration, and we'll see that the Slack configuration has the same base address as one that it kind of randomly hashed. And I have this local network, this FD00, which is one of those kind of non-routable local addresses. So I get a bunch of different IP6 addresses here. I also have that temporary address. So here's the FE80, the 9D72, blah, blah, blah. That's that local thing. And this doesn't show me the hardware addresses. Let's try to do the /all. Oh, wow, there we go. So I have a killer wireless, and it's there. Still doesn't show me my hardware address, but that's okay. So at home, I'm doing a lot more with IP6, mostly because Comcast is finally supporting it. And so what we can do now, if I try to ping one of these addresses, so for instance, if I try to ping ::1, we can see that I can just ping my local machine that's here. If I were to try to ping 2601:980 : I lost it, 980 C100 45:1. That's my local router, so this is going out over IP6 through the wireless. People think, well, maybe why aren't we using IP6? Maybe it's slower. Well, if I try to ping my local network over wireless, wow, it is slower. What the heck? I must be pinging that must be the Comcast side of my router, not my local router. Let me find out for sure, because that's a really bad example. RN6. So if I look at the routing table for my computer, here's the IP6 addresses, and yeah, so the .1 was the Comcast side. This is my local router here. So if I were to ping that address, if I can copy and paste, that should be the same performance. And it's not. I'm going to do some digging to see if that's a Windows thing, because IP6 should not be any difference in speed than the Windows, or than IP4. Anyway, this has gone on long enough. There's IP6 in a nutshell. We'll pick up again in looking at subnets.